All right, so pre-calculus 20, we are embarking on chapter 3 here. We'll do chapter 3.1 today, section 3.1. Chapter 3 is about quadratic functions. So in pre-calculus, in calculus obviously, quadratic functions are super important. There's a lot of applications, and so we need to understand quadratic functions. So we're taking an introductory view on quadratic functions and their features and how they're used and what they represent, that sort of thing. So you'll see in your textbook here, at the beginning of chapter 3, they talk about digital images and they talk about resolution, okay? So you guys probably know this, but a pixel is a picture element. And if you were to zoom in on a screen, any kind of digital screen, you would see, like this, that the screen is made up of hundreds or thousands or even millions of small squares that are each different color. So if you zoom in, and this is a good representation here, and you guys have probably all seen this before, like if the resolution is really, really low, it looks grainy, right? It doesn't look very fine-tuned. And each little square is one solid color. And so if you're trying to make a tree, you would want colors that are green or dark brown or something like that. And if you zoom out, that would look a lot like a tree. Now, this picture over here has 409,000 pixels. If it was a square image, it would be 640 along this way and 640 pixels high. And so a quadratic function is the simplest quadratic function would be y, or the amount of squares would be the amount of squares on one side times the amount of squares on the other side. And if those numbers were the same like this, if we had a square, then the function would be y equals x squared. So the number of pixels in a square image like this would be side length times side length, or y equals x squared. So we're talking about quadratic functions, which, this is sort of loosely connected to quadratic functions, but I think it's kind of interesting to know that the higher resolution that you have, there are literally just more pixels. So the squares are quite a bit smaller, so they can fit a whole bunch of other different colors in the same area for something that has higher resolution. And so the amount of pixels in that square would be much higher. Okay, you can read through career links and different things like that. So 3.1 is where we want to focus here, and we're investigating quadratic functions. I mentioned already that the simplest quadratic function really is y equals x squared. And that y would represent sort of the area, let's say, for a square that has dimensions x by x. Okay, y equals x squared. So we're going to look at the vertex form of a quadratic function today, and we're going to explore the parameters that you see in the vertex form. All right, so let's get over to the notes. I asked you to jot down some definitions here of bold-faced terms, so you can do that in as much detail in your own notes as you want. It'd be a good idea for you to summarize the things that are in the textbook, and if you can, in your own words, so that it makes a little bit more sense. But let's talk about it. So a quadratic function. A function whose value is given by a polynomial of degree 2. So you may remember that the degree of a polynomial, okay, if we have y equals x, this is degree 1 because the exponent on the x is 1. Y equals x squared is degree 2 because that's the largest exponent on the variable. Now, even if we had plus 3x minus 5, this is a degree 2 because the largest exponent on any variable in any term, or on the variable in any term, is 2. So we're talking about degree 2, okay, quadratic. This is linear, and y equals x cubed would be cubic function, and so on. So this is the quadratic. This is what we're focusing on, these ones here. You may remember, or you may know, that the shape, the general shape of a parabola, of a quadratic function, is parabolic. So it is a parabola. This is the shape. Parabolas exist in, I was going to say in nature. They do exist in nature a little bit, but in some flowers, okay, some flowering plants, if you notice that some of them kind of are shaped like this, and you have the flowers and stuff like that. Well, this would be a parabolic shape, meant to collect rainwater and all this sort of stuff, or whatever, sunlight. But that's not what I want to talk about. Have you ever seen at, let's say, sporting events, you see this dish, and it's a parabolic dish, and even satellite dishes and stuff like that, and they have a microphone or some kind of receiver sort of in the middle of this parabolic shape thing. And so what happens is it's meant to collect sound from a distance away, and the parabola is shaped in such a way, and this is maybe a more physics application, but the parabola is shaped in such a way that any incoming sound wave, the waves that are parallel, incoming to the dish, will all reflect to the same spot. Okay, and so this is what happens here. So all of these sound waves are collected, basically, into this place here, this spot here called the focus, and so the sound is amplified, and we're able to pick up sound. So you see on the side of football games, on the sidelines, they have these big dishes, these guys with the headphones on, and they're collecting the sounds from the field and feeding that into your TV set. So you can hear the quarterback, whenever you watch the football game, go, "Hey, say hot, hot." You know, you can hear all that. That's from that dish on the sideline. Okay? All right, so another main feature of a parabola is the vertex. So the vertex would be either the maximum point of a parabola, quadratic function, or the minimum point of a parabola. Now, parabolas can open upward or they can open downward. So this is obviously opening upward, and this is obviously opening downward. And we're going to talk about the parameters that cause this to happen. Okay, that's what we're going to talk about today. So some parabolas or some quadratic functions have a minimum, like this one over here, have a minimum value, and that would be the y value associated with the vertex, the lowest point. And some have a maximum value, and that would be the y value associated with the vertex of a parabola that opens downward. Okay. Now I realize I'm saying this kind of fast, and if you're completely unfamiliar with all this stuff and you're hearing it for the first time, I apologize. Please feel free to ask me questions later. But as some of you have reported that you've watched these videos over, and when you watch the video the second time, you pick up a lot of stuff that you might miss the first time. So I would encourage you all to watch these videos again, especially in preparing for a quiz or test or whatever, or if there's anything that you need to sharpen up on. All right, now another main thing that we need to talk about is the axis of symmetry. So when we're looking at a parabola, I don't know if you've noticed this yet, but there is a vertical line that passes through the vertex that would be a line of symmetry. And that's important when we're sketching, and important also to do certain calculations and to get information. But the axis of symmetry is what that line is called. It's a vertical line always, and it has the expression here, x equals. And x equals whatever it is the x value is that this vertical line passes through. It's also x equals the same value as the x value in the vertex. So that's what an axis of symmetry is. The axis, the vertical axis, and you see that it cuts this parabola exactly in half. Okay? It would fold over the axis right onto itself. All right. So those are some main pieces of the parabola. How many of you are hearing this for the first time? Is this brand new? Or is this something that you've maybe heard of this before? Okay, some of you. All right, let's talk about parameters. Now, again, we could have a parabola that looks different, right? It's positioned differently on the coordinate plane, and it opens, very narrow, very wide, or it opens down or up. So there are obviously different parameters that can be included into the equation of a quadratic function. And those parameters will change the orientation of it, the direction, the position of the vertex, and so on. So the simplest one that we talked about already is a y equals x squared. That's the simplest parabola. It opens upward, it's of normal width, and so on. So the vertex here on this very simple one is at 0, 0. Okay? And I actually have over here, where are we? On Desmos, I have a parabola programmed in here already. So this is y equals x squared, this black parabola right here. Okay? Now, I'm going to take this other one off. So here's y equals x squared. This is sort of what it looks like. I'm going to talk about some parameters, and that is how do we change that parabola. And the parameters are given in your textbook as a, p, and q. Okay? So let's talk about, before we see the form, let's talk about what A, P, and Q do. A affects A affects the width and the opening direction of the parabola. Okay? So the A value, and I mean maybe I could put this up on the same page here, okay? So this is the vertex form, which we'll get to in a minute, but the A value, if we change the A value, we can change how wide the parabola opens, and we can also change whether it opens upwards or downwards. Okay? So that's one part of the equation that we're going to see, and that's what it affects. The other one, the P value, is the X value of the vertex. So if you see the equation and you can identify what the P value is, that's the X value of the vertex. Or if you see the parabola and you see the vertex and you know the coordinates of the vertex, you know what the P value is then. It's the X coordinate. And the Q value is the Y value of the vertex. And because of this, because P and Q are both having to do with the vertex, this is actually called vertex form. Okay? Vertex form. So once again, there are parameters that affect the shape and position of a quadratic function, or the parabola that is the graph of a quadratic. Those parameters are labeled in your textbook here as A, P, and Q, and this is how they are situated in the equation. So y equals x squared, I have that in black. That's my original equation. If you have a number right here in this position that multiplies by this expression, this part here, that A value dictates the width and the direction of opening. The P value would be the number that would be subtracted from x inside the brackets before it's squared, and this number in here is the x value of the vertex. And then whatever is added to the outside of this squared part is the y value for the vertex. And we'll take some time to explore this as well. Now there is a little note here. A can't be 0. If A is 0, then we have a real problem. Then this is all 0, and guess what? If this is gone, if this is 0, we have y equals q, which is just a number, and so then we have a straight horizontal line. So this is not a quadratic function if A is allowed to be 0. So if A is 0, it's not a quadratic. All right. So let's take a look at Desmos here. So this is something that you can do at home or on your own time as well. I don't want you kind of looking at it right now. Let's all do it together. But Desmos is a way that we can graph functions. And also the neat part about Desmos, and I don't know if you can see this on the side of the screen if you're watching the video right now, but I can alter the parameters of the equation. So I've got an A slider down here. And look what happens if I move the A slider from A equals 1. If I move the A slider, whoops, I got to light this up, I guess. Hang on for a second. Okay. So if I move the slider, if A becomes greater than 1, look what happens to the parabola. Now the black one is y equals x squared. That's our base function. If I increase the value of A, then I get a very narrow parabola. Okay, so here's back to A equals 1 right here. And if A is between 0 and 1, I get a very wide parabola. Okay? So when you see an equation and you see that there's a number in front of the brackets with the x in it and the squared, then that number tells you whether it's wide or narrow. So what happens, how do I change this from going opening up to opening down? What do you think? What do you think I should change A to? Negative. Very good. You guys are on the ball. So again, here's a large positive A, and I'm coming down, and there's A equals 1, and then there's A equals 0.1. And now if A is 0, I have a straight line. But if A goes into the negatives, there we go. It starts to open downward. Okay? To negative 10. That's what it looks like. So I'm gonna let this A value move from negative 10 to positive 10, and you can see what's happening. Okay? So this is a very large positive number, and now it's coming back down. It's going to pass through 1 here, through 0, and down to negative 10. Okay? So, and when a equals 1, that is called a normal width for a parabola. That's normal. Okay? All right. So let me just go back to this screen here. I kind of hurried over this one, but now that we're talking about the width, okay, the parabola width is normal on this one because a equals 1. So when a equals 1, the width of the opening is called a normal opening. And here's how you can kind of tell from the graph. And not a lot of people, I don't think a lot of students really know this or remember this, but I'm going to tell you how to find a from the graph. Okay, so you should know how to do that. So if we go back to the graph, notice from the vertex here, which I have highlighted in purple, from the vertex, if you want to get to another point on the graph with this y equals x squared, if you go to the right or left 1 unit and you go up 1 unit, you have a point on the graph. So here's the point 1, 1. That's on a normally opened parabola. So if it has a normal width, you go from the vertex, you go over 1, up 1, boom. If it's a negative parabola, opens down, but it's a normal width, you go over 1, down 1, and you should be right on the graph. So what happens if a is 2? Well, I'm going to put a to 2 here. And on this green graph, this is y equals 2x squared. And so the width is over 1, up 2. See that? 1, 2. So if a is 2, then you would go from the vertex over 1 unit up 2. If a is 3, guess what you would do? You'd go over 1 and up 3, and you would have a point on your parabola. Okay? So this is just something that will help you later on if you're trying to find out what a is from the graph. Okay? Okay. Questions so far? Okay? You're all listening fairly intently here, so I'm assuming if there's no questions that you're okay so far. Or you're really not okay and you don't know where to start for asking questions. But I'll assume that you're sort of mostly with me, okay? All right, you may have questions a little bit later, which is fine. Okay, let's take a look at an example. So here's an example of a quadratic function, and I've identified the a, the p, and the q here in this example. So I want you to write this down, and I think there's at least one thing that I'm going to have to explain here. But in this example, it's pretty easy to see that a is 2, because this is the a position in front of the brackets where the x is and the squared is, right? So a is 2. Now, what do we know about this parabola then? Which way does it open? Up or down, do you think? Yeah, it opens up because the 2 is positive. Do you think the parabola is narrow or wide?
No.
Okay, narrow. That's very good, because if a is 2, you go over 1 unit and up 2 units. And that's going to be a little bit of a narrower parabola, whereas the original would be over 1, up 1, a little bit wider. Good. That's excellent. Now, let's skip over to q. Okay, if you have a minus 3 or minus something outside, then the q value is negative whatever that number is. This is really, really easy. Question? Quickly. Yeah. And so that means that the vertex, the y value for the vertex is at negative 3. Okay? So this is y value of the vertex. Now, I want to focus on p here, because this is where students forget that they have to do a little switcheroo here. Notice that the form, boys, notice that the form of this graph, or this equation, is x minus p. Okay? If you have x minus p as the format, then when you have something like this, x plus 1, what you have to understand is that that really is, I'm just going to erase some things here. Okay? So that really is x minus a negative 1. You see that? So here's the format. It has to be a negative. So what is the p-value? Well, it's really opposite of whatever you see here. The p-value is the opposite sign of whatever you see inside here. Okay? Opposite. Got it? So what's the vertex of this parabola? Well, if we look closely at the equation, the vertex should be -1, -3. So that's the strength of this form, is that you can easily see the vertex. You can also easily see the direction that it opens, and you can easily see sort of relatively how narrow or wide it is. Okay? So I'm gonna put this into Desmos. Y equals 2 times x plus 1 all squared minus 3. 2x plus 1. So y equals 2, so I'm going to move my slider down here to 2. X minus 1, so that means that p is going to be plus 1. And notice, see when I'm moving p there, I didn't actually do this for you yet, but you see how it moves the vertex left or right? So here's p equals, oh, it was plus 1, so it has to be -1. Right? Yeah, p plus 1, so p is -1. And then the q is -3. So notice when I move the q to the left, there's the vertex. All right. So this is y equals 2 times x plus 1 all squared minus 3. And here's the vertex, and it is at, okay, well, I thought it would be labeled there, but it's -1, -3. Okay, that's what it looks like. So we were correct. Any questions? Okay, so that a value makes it narrow or wide, and the p-values move the vertex left to right or up and down. You guys good so far? All right. Okay, so on page 146 here, this is the effect of A, and you can see a few graphs all in the same coordinate plane here. F of x equals x squared is the blue one. If you have an A value that's between 0 and 1, then it's a little bit wider. And if you have an A value that's negative, it opens down. And if that A value is actually greater than 1, the value itself, then it's narrow. If we're talking about the q outside of the x squared, that moves the vertex up and down, because that's, remember, the y value of the vertex. So moving the q, if it's plus 5, it goes up 5 units. The shape doesn't change, just the position of it, okay? And then if you go down, if it's a minus 4 there, it goes down. Now, the p-value of the vertex, this value is inside the brackets with the x, okay? Very important. It's inside the brackets with the x, and if it shows up as an x minus 1, that means the whole parabola moves to the right 1 unit. So an x minus 1 means it's kind of like opposite, right? It means right 1 unit. If you see x plus 3, that means it's moving left. So here's the graphs right here. X plus 3 all squared, the parabola moves from 0, 0 left 3 units. Okay? And so we did take a look, I think at an example here, right here, that I copied. Okay? All right, that's the one we just looked at. All right. Okay, so the parameters. Hopefully you understand what the parameters do. Let's take a look at example 2 now. Let's look carefully at this graph. So determine the quadratic function in vertex form for each graph. So if we were to do that, we would want to find out where the vertex is. Okay? So given a graph, oh, come now. There we go. So what we want to do is we want to locate the vertex first of all. So what is the vertex here? It is over how many units? over 5 units, so that's a positive 5, and down 4 units. So does everyone see that the vertex of this parabola is over 5 units from 0, 0, over 5, and down 4 units? Everyone see that? And so the vertex is at the point 5, negative 4. You guys good with that? Identifying the vertex from a graph? Okay, I'll assume you are. Hearing no objections. Now let's take a look at the width. Okay. Now sometimes this is actually really tough to do, but let's see if we can figure it out from the graph. So we could go over 1. Ooh, and a normally opening width would be up 1 as well. So do we have a normally opened width? No. So A is not 1. Okay. So from the graph, we actually could do a couple things. So this is really tough to tell, but the A value is actually, if you go over 1 unit, the exact height that you'd have to go up to get to the graph, that's actually the A value. Now it's actually pretty difficult to tell because we don't know how far up we had to go there. So we could make a guess of like maybe 1/4, I don't know, 1/2, I don't know what it is, 1/3 maybe. So we don't know exactly, but we could use these other points as well. So you see there's 2 points given here. Okay? Now, what are these 2 points? This is 8, -1, and this is 2, -1. Right? So we could go 1, 2, 3 units up, and 1, 2 over, and 3 units up. Does that help us at all? Does that help us at all? So, boys, how far would we have to go up normally on a y equals x squared graph? So over 1, up 1. If we went over 2 units, how many units would we have to go up? So if we went over 1 unit, we would go up 1 unit. If we went over 2 units, how many units would we have to go up? 4. Remember, this is a squared term, right? If we went over 4 units from 0, so if x would equal 4, how many units should I have to go up? 16. So if I went over 3 units, how many units from the vertex would 3 units, how many units would I have to go up in order to hit a normally distributed graph or normally opened graph? I should have to go up 9. So this is really important, okay? This is maybe kind of tough, and this is not the only way to do this, but this is one way. So if I had to go up 9 units on a normally opened width, and I only have to go up 3, what is 3 out of 9 in comparison? 6, 7, 8, 9. So this is where I would normally go. This is the normally opened width right here. So guess what? This is 3 over 9, or 1/3. It's depressed by 1/3. Okay? So this gives us a hint as to what this actual A value is. Now check your textbooks out. Okay, so one of the other ways that you could solve for A is algebraically. So if we just take a look at this, y equals ax minus p squared plus q. That's our format. All right. So what's the vertex here? The vertex is actually 5, what do we say? 5, -4, right? So this is what we can write this as, x minus 5 squared minus 4. That is putting the vertex into the equation. Okay? Now, I'm getting close to solving for A. If only I had one other point that I knew was on the graph, I could solve for A. So notice this, that if you plug in a value for a known point on the graph, so an x value and a y value for any point that you know is on the graph, you would only have A to solve for. And so guess what? We could use any one of these points that we know of. Here's one. The point is x equals 2 and y equals -1. So if I plug those values in, -1 there, I don't know what a is. I know that x is 2. Now I can solve for a. Alright, so once again, we have the vertex inputted into our format. Now I can plug one other point in and get an x and a y value for another point that coincides with the graph, and I could solve for a. So this is the algebraic method, and let's see what happens. Okay, let's add 4 to both sides, so that's going to be 3 over here. What's 2 minus 5? That's going to be negative 3. Okay, so I'm going to have to square negative 3. That's going to be 3 equals positive 9a. Divide both sides by 9, and a is equal to 1/3, and that is exactly what we got from the graph there before. So the last thing we'll talk about today in this lesson is determining how many x-intercepts could be possible given the equation of a line. So let's just say, of a parabola. So let's just say we have this. We have 2 times x minus 4 all squared plus 5. Okay, so before we dig into this, before we dig into that, let's just see what our options might be. So if we had a parabola could open up or down. A parabola's vertex could be above the x-axis or below the x-axis or right on the x-axis, right? So let's just see. Let's say we have a parabola that opens upward and has a vertex or a y value for a vertex that's above the x-axis. How many x-intercepts would there be for this parabola? None. That's right. There'd be 0 x-intercepts. What about for this parabola where the vertex is right on the x-axis? How many? Yeah, we would have 1 x-intercept. What about for this one where we have it opens upward and the vertex is below the y-intercept? This is 2. I'm not sure why. 2. Okay, so that's what's possible. Now, you can probably envision that this would work as well for parabolas that open the other way, right? So if we went like this, and like this, and like this, okay? 1, 2, and 0. So what we have to do is we have to figure out, okay, where the vertex is and the direction that it opens. That's all we got to find out. Then we know how many intercepts that there are. So the vertex here, for this example, I'll do this back in red. What's the vertex here? Somebody shout it out if you know. The coordinates for the vertex. So we're looking here and we're looking here.
4 minus 5.
Positive 4 and positive 5. So it's the opposite sign here, but the same sign here. Okay? So 4, 5. So we're going over 4, we're going up 5. Here's the vertex. Is this parabola opening upward or downward? Upward. Very good. Totally redeemed yourself there. Awesome. So how many intercepts for this particular function right here? How many intercepts? 0. It opens up and it's above the x-axis. So 0. Does that make sense? Okay. All right. That's good. I'll give you a couple more examples. How many intercepts for this one? How many intercepts for this one? What's the vertex? Or really, more importantly, all you have to do is examine the y value and the direction of opening, right? That's all you got to do. So this y value for the vertex is above the x-axis, somewhere up here. Actually, it's over here, but it doesn't matter. It's above, and it opens what? It opens downwards. So we're going to have how many intercepts? 2. Awesome. You guys are good. Okay, one more. I'll give you a tricky one. Y equals negative 0.5 x plus 10 squared. That's it right there. How many intercepts there? 2? Anybody agree or disagree? Agree or disagree? Who disagrees? Hint, hint. Okay, so where is the vertex? What's the vertex here? It is negative 10, comma what? 0. So that means it is on the x-axis. Which way does it open? Doesn't matter, does it, actually? But it opens down and it's wide. So there is one intercept. Okay? One intercept. All right. All right, grade 11. So here are your key ideas. Please take a moment to look at these. The class is almost over. Sorry, we took up most of the class for this lesson. And I will give you some homework questions to begin working on. But you do have your test coming up soon, right, for chapter 2. So, but that's not till what, Tuesday? So, yeah, this will be due. I'll give you about half the assignment probably to be due Monday at least. Okay, so I don't overload you this weekend. But here are the notes there for 3.1.
My bad.
Magic monkey.